My name is Jason Murray. I'm the CEO and co-founder of Shipium. To kind of understand what Shipium is, I want to talk a little bit about my background, kind of the road that got me here. I spent 20 years at Amazon, and my career was largely focused on the merger of logistics and technology. Early days, I worked on the fulfillment center technology around labor management, picking, packing, that kind of stuff inside the building. But around 2010, I went on this journey to build out this organization called Supply Chain Optimization Tech, and that happened to kind of correspond to the same time that Prime was starting to take off. And so Scott, what we called it internal to Amazon, was responsible for the coordination and optimization of all things supply chain at Amazon. And it had kind of all of the decisioning around demand forecasting, how we thought about inventory positioning, keeping it closer to the customers, um, the promise that we told to the customers, kind of what speed we were telling them in terms of when things would be delivered, the order flow through the network, and how we kind of maintained inventory position, and then even the back end transportation optimization around how do we get it to the customer to make sure we're hitting that promise. And so that layer of software really became the impetus for what Shipium is. When I left Amazon in 2018, kind of looking around, the thing was that this software, this kind of stack of software, was totally missing from the larger ecosystem. And one thing to kind of note is that this is something that kind of lives outside of the traditional TMS, OMS, WMS. We obviously had those at Amazon, but this layer of software acted as this coordination layer, and the magic of that whole interaction was what made the whole thing go. So I wanted to, before I jump on to kind of talking about some of the stuff in more detail, I just want to talk about kind of how we thought about the stack in general. Where did we get to over years of iterating on what makes sense at Amazon, and kind of what makes this different than the kind of what's available now. And I think first and foremost, everyone is aware of Amazon's obsession with the customer. And I think one of the things that really stands out to me that we did a good job with at Amazon related to this technology stack was that it was totally focused on the customer from the get-go. So instead of thinking about when things are going to ship, we were always thinking about when they were going to be delivered, right? So totally customer focused, built from the ground up to support that modality. The second piece was really around kind of how we thought about optimization. When we started on this journey in 2010, that was when a lot of the machine learning, people are now referring to as AI, was coming online, and what we were essentially doing was taking kind of what would be considered traditional operations research, where you're doing these optimizations, and we were applying machine learning techniques to that, and it actually ended up being a great lever for us to continue to kind of improve the granularity and fidelity of this optimization. So we were looking at customer data in terms of how they were interacting with the website. We were looking at the transportation networks and how they were performing, how they were structured, and then building all these models that ultimately led to cost savings, but also kind of back to the first point, allowed us to give more transparency and more precision around what we were telling the customer. But then the last piece, I think, which is really critical, is this notion of automation. And from very early in my journey in Scott, we focused a lot on how much of the system is running this all on its own versus what it's being run by humans, right? And automation ends up being this great proxy for how much is the system being used. So you can build these optimizations, but if you're not automated, no one's actually using this technology. But it also ends up being this proxy for if you do automate these systems, you end up with this situation where you have more room for strategic focus, right? And so after we automated the basic pieces, then that led to things like starting to use these systems for network planning, or even how we thought about cost structures in Amazon transportation, et cetera. So I think for your journey, we don't expect that everyone's journey is going to look just like this, but I think these three tenets around what makes a solid supply chain and how you should structure and think about it really hold for just about anyone who's working in this space. So I'll move to the next slide here. I think before I go any further, it's probably worth kind of talking a little bit about kind of the latest influx of generative AI versus kind of what you would call traditional ML. Um, I think the to some degree, uh, a lot of people would almost refer to the generative AI stuff as a subset of machine learning, right? And it's obviously working within the bounds. It's taking a massive data set, more than the world's ever seen, and applying these relationships between language that it's processing through from the internet. I don't actually believe that this is particularly useful for the space that we're working in, and the reason is because the space that we're working in is much more mathematical, much more precise in terms of numbers, et cetera. And so, if you're doing something like trying to measure the time in transit through a transportation network, you wouldn't want to kind of convert it first back to language and then try to push it back the other way, right? It makes a lot more sense to just think about it as a mathematical optimization on top of this data set that you're working with, right? Which there's virtues in both. I mean, obviously having more access to more processing power and the things that have kind of enabled Gen AI is obviously a tailwind for the work we're doing in kind of machine learning, supply chain optimization stuff. But it's not a one-to-one fit, right? But that's not to say it's not useful. It was useful back in the early 2010s when we started working on it. It's become more useful as more techniques have been developed, et cetera. And we see this as the more data that keeps kind of coming into the more data that becomes available in these systems, the better job we're going to be able to do with predictability on the back end, which is obviously a huge part of supply chain decision making. So kind of moving on to the next slide, I just wanted to walk through quickly how we think about like kind of the timing of how this stuff happened and the journey that you really end up going through. This isn't, some of this is kind of coming from my memory. Some of it's not super precise, but the point here is that um, models beget models, and what we saw a lot at Amazon was you have to kind of take that first jump, start working with some basic models, and then that leads to more decisions at the Zuber level, right? So, walking through my particular timeline, we had a system called Atrops that was modeling out this is what the timing in the transportation network looks like, and we're going to use machine learning to kind of um, figure out how between nodes the timing of the flows and how long carriers take, et cetera. That led to starting to basically use this transportation data to fulfill prime orders with things like USPS or UPS Ground, right, where we could save money. We were ultimately then took that data and started rolling it into how we think about network planning. We rolled this into the decision making on how you think about draining inventory out of the network in terms of deciding where to ship things from. We were using these transportation paths and that to kind of search through this tree of if I do decide to ship these two items from this building, how long is it going to take to get to the customer versus how long if I ship these two items from this other building, or what if I split between the two and then match that up with a cost. So, and then eventually all of that led to kind of how do we think about optimizing search to basically move things up that are closer to the customer so that they're obviously receiving a better experience. So this is not a precise mapping, but it just talks about once you kind of enter this world of data science and you're starting to use predictive analytics inside of your organization, you're going to see it all flow up. You're going to see more and more things be built on top of that, and that's really the journey that we're starting to see our customers go on, and it's going to be very exciting to see this kind of evolve over the next 10, 15 years. So, so I think it's also worth, before I go any further, to just talk a little bit about why um, the whole notion of why are we even using these probabilistic systems in the first place, just to kind of level set a little bit. I think, when I first got out of school, the prominent thing, and even AI at the time, was all about kind of rules, right? Where you're saying, if this, do this, if this, do this, if, I'm going to map these specific points. And the problem with that methodology is eventually they start collapsing on one another, and the complexity monster comes in, and you can't possibly kind of the trees of all these become longer and longer. And it's impossible to kind of actually map out every possible scenario. And one of the reasons for that, programming languages are very, very good at precise structure. That's kind of why they were designed. That's why we don't program in English. We program in these programming languages because they're very, very precise, but they're not good at kind of understanding um, stochastic information in the system. And a lot of these decisions, they're really by nature stochastic or probabilistic, right? Meaning that it's not a actual sure thing. If I look on this chart I have here, we don't really know what the effect of the blizzard in Chicago is. There's a chance, the timing of that network is not for sure. These are physical processes, and so thinking about these things as stochastic processes, where there's a chance that it won't, 95% of the time it's gonna flow through in this timing, but 5% of the time it won't. Then you can use traditional techniques for combining these stochastic variables together to kind of get better outcomes, and that's really what this is all about. You're representing things as they match. That something like a cost structure is something that's deterministic, precise, etc. Stochastic things are like, how long is it going to take to flow through this network? And so by explicitly mapping them to what they are, then you use the specific tool to actually come up with, okay, if I do deliver to this customer, there's a 92% chance it's going to get there by this date, right? And then you're able to kind of make your decision based on that. And so this is how we kind of think about these problems. You break them up into the right representation of what they are, and then move from there.
All right, so let's walk through Shipium's demo of a real-time time and transit model that customers use today live on the platform. So what we're looking at here is a map. The map shows on the upstate what the time and transit model would look like using kind of a more conventional aspect of static tables that a carrier typically issues. For reference, what we're looking at here is it is a Shipium customer that's very real. They have two warehouses, one on the East Coast, one on the West Coast. Within that, they have some of the national carriers. They haven't yet gone in terms of adding a regional carrier. And their volume is somewhere in that 3 to 5 million per year shipment range. So this map shows a time and transit table that they would use kind of in a pre-Shipium world of how they think about the delivery times. This often powers an EDD that you would see through their WMS, like Manhattan or Blue Yonder or Corber, paired with inventory, so it's very static. It's also what would be used in terms of rate shopping if a particular deliver by date is used. Before I advance to the next slide, you can kind of see here what the time of transit is related to population per county. And the interesting thing here is how there's over 24 or 21% that are 4 days and then higher. Ready? So now let's switch over to what this customer is using live right now on the platform. So this is our time and transit model that is powered by real-time ML versus the static SLAs from carriers. So first, if I work backwards, right? So now let's look at the percentages. We went from over 21% of the population would see a 4-day or later estimated delivery date. Instead, that now shifts to under 2%. So 98% of the population would now see a 3-day or faster delivery date on their website. So first, let's pause and think about that. That's insane, right? Because what this customer is now doing is it's able to more reliably give a 3-day date as the delivery promise window that they weren't even really sure they could hit prior, right? And then if we think about what shifts, it's mostly in the middle part of the country, right? So there still is a lot of 2-day action near the West Coast warehouse and near the East Coast warehouse. The changes is that the variability is a feature, not a bug. So there's part of Appalachia that is still a little tough to hit. You just never know with the networks. It's hard to manage that in particular on your own. You need the model. But so much of the Midwest, the Great Plains, the Southeast, they all switched over to more of a 3-day date. So that's awesome. So now let's think about what happens here with what's simulating the future might look like. So here we have the same exact concept, which again, this is a retailer that's doing roughly 3 to 5 million annual shipments. They have an East Coast, West Coast warehouse. They were using just a handful of nationals plus USPS. And what you saw was a snapshot at August 1st. It was frozen, the P90 time and transit table powered by ML. Because it's a model, though, you can really change it to anything, right? So this is taking the same exact profile and setup that I just said and now injecting a hypothetical origin in Nashville. And what this does is it changes the makeup considerably. You get a lot more 2 days kind of in the Midwest and the Southeast. It doesn't seem to impact Appalachia as much. And it didn't have nearly as much impact in terms of taking away the last remaining 4 days, but that's okay. So this is the power of simulation, because you can now see or project what things are going to be with confidence before actually making the decision of, say, opening a warehouse in Nashville. And it can keep snowballing. So now let's move to the next one, which is what happens if they add a regional carrier. So this is hypothetically adding the carrier in the Northeast. It is a carrier where they got a rate table from. And by adding this carrier, because it's one already on the Shipium network, already being used for millions of shipments, it's a regional carrier, we can take that and stochastically model how it would impact the delivery network of this customer if they were to add them by effectively adding them into the model. Pretty amazing, the overall shift of 3-day to 2-day, and just a considerable impact in terms of the population. So that's interesting. And now lastly, if we adjust this by adding 5 stores, so these are 5 example stores that we pulled out. And if we take those addresses and hypothetically add them in, and basically there's a whole bunch of rules you can do in terms of simulation. We're just doing this very, very basic where the rules or the assumptions would be that all of the national carriers are available from the stores. And the only regional carrier we added, which was this hypothetical in the Northeast, is just still to that Northeast warehouse. So with all the nationals picking up and delivering from the stores, you can see how this impact. And I mean, the story here is you're basically looking at over 3/4 of the population can now get a 2-day date. That's pretty competitive. So let's talk about some real world applicability of what we just watched. We can do this with one of the more basic use cases out there, which is rate shopping. We like to say that there's these kind of 3 stages of a modern day rate shopping, which Gartner would agree with us in terms of their maturity model for it. We use it as kind of the dad joke of you gate shop and then date shop, and then at that point you rate shop. So the gate shopping first is really just checking for eligibility. What this means is that if you have the right technology in place, you can take a look at things like package level details, so you shouldn't put batteries inside of air methods, things like that. But also, if you're going to add regional carriers, you need to know which addresses they can deliver to. You need to have kind of some more standard rules out there, like carrier volume limits. So if FedEx can only do 10,000 shipments this month from this warehouse, how do you manage that in your logic? But also, this is where a lot of custom rules will exist, and the ability to kind of turn them on and turn them off with ease. So checking first the eligibility of carriers, you then move to the date shopping side of it. Certainly date shopping is not a truly novel or new concept. You can certainly pick a carrier service method based off of some sort of a date constraint. The interesting concept, though, over history is that the date constraint is usually tied to either a carrier SLA, so a 5-day ground has a 5-day SLA, or tied to a static time and transit tables that you would get from a carrier. That is what I showed in that first slide. And those are always difficult to use because they don't have any sort of real-time or dynamic aspects to them. You don't know if 7 p.m. on a Friday is different than 7 a.m. on a Monday, or 7 a.m. on Cyber Monday, or 10 days before Christmas, or there's a blizzard in Chicago, or all these factors that should come into it. All you know is that, sure, 5-day ground takes 3 days to go from Reno to San Francisco, and that's the static table they give you, but you don't know in real time. So the point of this date shopping phase is that if you use this ML model and apply it to the rate shopping process, you can now much more accurately in real time project which eligible carriers might actually hit that date. This is a really powerful way to reduce a lot of costs, and in particular with economy methods, which we'll get to in just a second. And then you get to the actual rate shop, which is of those who are eligible and those who will hit the date, who's going to have the cheapest fully loaded rate, which includes all accessorials and what may be off book, things like that. So when we get to the areas that you can apply this that have some real world business value, a really good example are economy service methods. UPS MI is a good example, DHL Ecom, things like that. Economy service methods have a lot of value because they're often going to be the most competitive on price, but they have some challenges in the sense that they don't have an SLA given to them, and they often don't even publish a time and transit table that a customer can use. So they're largely gated out of any sort of rate shopping process that has any sort of a date constraint, even if the date constraint is like 5 days or something like that, right? So that's kind of a cool thing with ML here is that you can actually find areas to apply it to a data set that didn't exist prior and effectively give an SLA, so to speak, to these economy methods and now use them in your rate shopping process. A good example is this case study, which does that. And what happened is that they're a large Fortune 500 retailer. They do a whole bunch of stuff from apparel to home goods and appliances, things like that. They're in North America. They used the nationals in terms of a carrier network and then added 3 regionals. But they had 2 economy methods within that. There was very little volume going to it. They wanted to deploy more of kind of a premium customer concept to trial it before they went to marketing and things like that. So they were applying these delivery dates, and what they found was astounding, which is that there was actually a lot of volume that could be going to these economy service methods that were tagged with this premium customer concept that had a 3-day delivery date constraint. So the result was way more of this volume shifting over to economy methods than they thought, that they ended up seeing almost $30 million in savings. So when we think about how to structure this so that you can actually deploy ML models in a way that your business can use, we think about these core concepts, also principles. The first is that if you want to feed these algorithms, you need historical performance data. This is the best data set that you can get. So if you're doing shipping, which is our presentation here, if you're going to do ML on time and transit, you need historical shipping data. The interesting thing, though, is if you go to the second principle, is it's not just your historical shipping data. You need a lot of historical shipping data, especially for a lot of carriers, maybe even the ones you don't even use, right? So if you go back to that simulation aspect, this customer would have had no idea whether or not to use this regional carrier in the Northeast, except for the fact that we had them on the network and other customers were using them for millions and millions of shipments, that we could project what their time and transit value would be for a certain subset or a profile of shipments. The best way to think about this is that you can do more together than you can do by yourself. And the best way to feed the data algorithms that will power your unique part of the business is to lean on solutions or others that have figured out a way to just leverage a bigger data set than what you have available to you. So assuming you have all of that, the next is you need to do this really interesting thing that honestly no one is really doing right now, which is connecting the execution system to the analytics system. I think the world has a lot of really wonderful analytics tools out there. They've been hanging around and improving and innovating since the 90s. The interesting thing, though, is that there's sort of this like assembly line way, old school way of attacking this, which is they get the data, they produce the data, analysts look at the data, they make a call, and then that's it. It kind of ends there. To implement those insights via analytics, it's very difficult because the connection to the execution systems doesn't exist. Those systems that are doing the rate shopping, that are doing the business rules, that are doing the manifestation and label generation, et cetera, they're just like way off to the side, right? And they can't really be informed by the analytic systems. If you connect those two systems, then you can have confidence that what you're seeing on the data side will be applied terms of the decision making. So how you get to all of that is effectively interoperability and centralization. Like if you have 6 warehouses, you can't have 6 different shipping execution systems that are harboring all of their data on their on-premise VM in the closet and not letting that get pulled back into some sort of a warehouse that is powering a lot of your ML modeling. Here's the most basic of examples that is really one of the key value propositions and powers of Shipium, which is this dynamic time in transit model, but applying it across multiple solutions or systems within your existing technology stack. So what you can do is if you have this model that takes point A to point B in real time at any point of the day, day of week, day of year, and then whatever other constraints might exist in terms of rules or weather patterns or whatever, right? If that exists, you can now pipe that via API calls, not just in the rate shopping that we talked about, but why not pull it upstream a little bit to your OMS? So now the order routing can be much better informed on how to route the order by this model. And this is the main way that we work with our OMS partners like Manhattan and Blue Yonder, is that they are the system of record and the authority on inventory and markdowns and everything else that matters. But now, just like you offload from your brain to a calculator, they offload to Shipium what the probable time in transit and cost of that is going to be so that their fulfillment planning and order routing is much better informed to improve your outcomes as a business. And keep going a little farther up. Now you're looking at things like EDDs on the website, and you can pair the inventory availability, especially in like a multi-SKU type of order or cart, with this dynamic time in transit model so that you just have much higher accurate EDDs that are going to customers.
So thanks, Chris. Just to wrap up, I want to kind of reemphasize a couple points. So first of all, I think that if you are not taking advantage of kind of data science in your enterprise, you're missing out. I think this is it's solving a lot of problems that have traditionally been very hard for humans and computer systems to solve. And so I think this is going to continue to have a bigger and bigger impact on supply chain. It already has, but it's going to continue to be a bigger, bigger thing. I think you want to focus on predictive ML and things that are actually solutions targeted for the problem, as opposed to trying to jump on the Gen AI bandwagon. I think there's opportunity almost in every enterprise that we've talked to. All of our customers share the same thing. There's data that is interesting in terms of improving outcomes of your supply chain. And what you're going to want to do is use these machine learning techniques to kind of fill the gaps in and basically turn that data stream into something that's predictive and helps you make better decisions for your customers. Something like, in our case, the example I keep going back to over and over again, using transportation data as a means to understand how long it takes to get through your transportation network in reality. So we recommend, obviously, partner with shipping technology, partner with companies that specialize this if you don't have in-house knowledge about how to deal with this. And then secondly, when you do evaluate platforms, make sure that you choose platforms that are heavy on the data science side, because this is going to be a baseline requirement to be competitive and successful in the years to come.